This episode of the Amp Hour is sponsored by Rohde & Schwarz, a leading manufacturer of value instruments designed to help you maximize your bench's performance for everyday applications. They just announced an industry first, complete solutions with all the upgrades up front for one price. Now through December 31st, save up to $10,000 on Rohde & Schwarz solution packages that come with fully loaded test and measurement instruments right from the start. When you invest in Rohde & Schwarz products, you get the highest quality engineering, plus all the bandwidth, channels, inputs, memory interfaces, and signal generation you'll ever need. Learn more about Rohde & Schwarz value instruments and this limited time promotion at askanengineer.us. That's askanengineer.us. This is the Amp Hour Podcast. Released June 9th, 2019. Episode 446. An interview with Pete Bevelaqua. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
Hey, and I'm Pete Bevelaqua of AntennaTheory.com.
Hey, Pete, how you doing?
Pretty good. How are you?
It's good to talk to you. I've been scouring the internet to learn more about RF these days, and came upon your site and remembered that I know this guy.
Yeah.
I'd met you. You gave a talk at HDDG back a couple years ago now.
Yeah, that was fun. I was building a VNA, so Vector Network Analyzer, which is actually one of the most critical tools for measuring RF or antenna. Mm-hmm. So I just kind of frustrated at the super high cost, decided to build my own, and ended up hanging out with you guys for a while.
Yeah, that was good. It's a great talk. We'll definitely link it in as well. Well, let's start back. How did you get into this? So you are an antenna designer
Yes.
For various. So can you list some of the places you've designed antennas in the past?
Yeah. So I worked at Boeing originally doing defense, and antenna design there is more about like minimizing coupling between antenna systems as opposed to design, because they just have a lot of space. Then I went to Apple, was there for several years, worked on the Mac Mini and a bunch of different iPhones, some other stuff. Was at Nest for a while, did different things there, and worked on some wearables as well. So a lot of consumer electronics mainly, but familiar with defense and other various applications.
Yeah. And so did you get started at the beginning of your career? Like, were you always like, no, RF's where it's at, that's where I'm going into? Like, where did you get started in all this?
Yeah. So taking it from the time I started as like going into electrical engineering, I really liked like electromagnetics. And so I was just kind of drawn to that. I like that more than like circuit design, for instance. So I kind of liked just the math-based problem solving. I thought it was cool. And I didn't know much about antennas at the time, but so I was taking like those classes as an undergrad. I went to Stanford for my master's, and I took an antenna class, but it was really bad.
Oh, really?
Yeah. So like I came out of there, and I remember thinking like, I don't know much about antennas, because it was really theoretical. It was like,
sure,
here's a show that the fields from a small loop antenna are the same as a small dipole antenna if you switched H and E. And it's like, okay, that's cool. Can I design an antenna? Nope.
Yeah, like, when do I need to do this in the real world, right?
Well, and just the fact that like, you take the class and you do well, but you come out and it's like, do I know how to put an antenna in a phone? And the answer is no.
Yeah.
And so I wasn't. So then, I was kind of into signal processing for a while, and it just so happened I ended up at Arizona State, and there's a famous antenna professor, Balanis, who wrote like an antenna textbook. So I started chatting with him and ended up joining his research group. And so my PhD is like able to combine like signal processing stuff, like convex optimization techniques, to antenna array optimization, and ended up fitting together really well. So I was able to, kind of merge two fields in a way that hadn't quite intersected yet. So that was pretty cool.
Yeah.
But yeah, so it wasn't like I loved antennas or knew that I was going to do antennas. It was, I had an interest in electromagnetics, and then antenna opportunities just started coming up. So then when I was looking for work, like Boeing antenna engineer was there, and just kept going.
Yeah, that's great. So tell me about ASU. I mean, so the research, I didn't quite understand what you were talking about there. So the convex piece, what was that?
Yeah, so at Stanford, they have like a really big convex optimization program, or like the leader in convex optimization research works there, and it's part of the EE department. It's basically like a really kind of general class of problems where you can guarantee a global optimum solution if you can frame a problem in a certain way, which is convex. So like optimization problems are basically like minimize an objective function subject to some constraint. And a convex optimization problem means the objective function is convex and the constraint set forms a convex set. With those two properties, it's actually really like broad class of problems, and you can guarantee a global optimal solution, which is super useful. So anyway, so when I went to Arizona State, I started working on antenna arrays and figuring out like how can we make the lowest possible, side lobes given a beam width for a fixed number of elements or whatever. I was able to apply this, convex stuff to antennas and write some cool papers.
Yeah, and so that's kind of what pairing up that what sounds like very theoretical, the convex optimization, with the practical, like you're saying. Could you give some more examples of how the convex optimization might be used in the real world, like on a daily basis?
It's used a ton in signal processing. So finding weights that, like, there's probably optimization algorithms and, all the, how our voice is being processed right now.
Void codec or something.
Yeah. So I'm not super familiar with like all the applications, but, at least in for antenna arrays, we're able to apply it to, determining optimum weights and corresponding optimum positions that work together.
Okay. And does this relate to like matrix math around the optimizations? Is that the convex piece?
Okay. Well, so if you have like a constraint set, like AX is less than or equal to B, where X is your, variables you're optimizing over, that's like linear optimization. So there's like a whole set of optimization problems called linear programs. And so then you would have like matrix constraints and stuff. So convex is just a bit more general than that.
Okay. Huh. That's great. Yeah, because it's interesting to me. Like I feel like a lot of the math that is inside of like a lot of the field solvers and all the stuff that's out there, it's kind of hidden from people that are using them on a daily basis. But having that like low level understanding, like you're talking about, could be really useful from knowing what to tweak and how to tweak it.
Yeah,
that's great. Okay. So Boeing, I've heard of this Boeing.
Yeah.
So you had mentioned that it was like it was about making sure that you don't interfere with one radio to the next.
Particularly like on the defense side. So, okay. So they'll be like, oh, we want to take a certain airplane and we want to add like 20 antenna systems to it.
Oh my God.
All right. Because that's what they do, right? They have just a ton of radars and communication systems with everything, like all sorts of GPS stuff, just, satellite every communication system you can think of, they'll put on there. And so an airplane is pretty big. So, you're not necessarily like space constrained. But so like what we would do there is we spent a lot of time like, okay, if we put the antennas here, this is our field of view. And so it's like what locations are not obscured by the wing or, tail or whatever. And then figure out like, okay, what's the coupling between these two systems? Because that'll determine like whether they can work at the same time, coexistence, or what level of filtering you need to enable them to work at the same time.
Okay. Yeah. And like what are some of the frequency ranges that we're like talking about here? Like
for military, well, they always say DC to daylight, but what that means is I would say like 20 megahertz on the low end to like 40 gigahertz or a little bit higher on the high end. But.
Yeah. Wow. Okay. And that was the same thing where you had to figure out like, is the 20 megahertz interfering with 40 gigahertz and all that kind of stuff?
Yeah.
Too?
Well, in that case, there's so much frequency space, you're probably okay. But like some of the radars would have like, blast like kilowatts of power, which is
right.
60 dBm. Then we have like a radio next to it whose sensitivity is like minus 110 dBm, for instance. And, so you might have need like 200 dB of filtering or something, and that's where
Right.
you're like, okay, we can't operate these systems at the same time.
Right. Yeah, and I mean, so you also run the Antenna Theory website and stuff like that, and
Yeah.
so like when you are thinking about getting people started in this kind of stuff too, like so just talking about like filtering and antenna theory and everything else, where do you usually have people start? So like that question I just had about like you know low frequency versus high frequency and how they interact and stuff like that. Like how is it where do you usually tell people to kind of to get into that element of things?
Yeah. So, I mean, I would say like everyone's going to start with a specific problem and then kind of dig into it there. So, like a lot of people are like, hey, I want to put a Bluetooth antenna in my device. And so there you want to understand like just the fundamental rules of antenna design. Like, hey, having a half wavelength is good. Don't put metal right behind your antenna. And, if you're on the other side, like RF, where you're like, hey, I want to know if two systems work at the same time, then you say, okay, well, here's the two frequencies, figure out like what the roll off of the transmitter is from your data sheet and what the sensitivity is on the other side, figure out like what level of filtering there is, search DigiKey to see if you can find a filter with those parameters, So a lot of it is like you have to start like with the specific problem in mind, like the whole, like if you just want to learn antennas in general, then yeah, I'd say go to the antennatheory.com and just start flipping through it and learn the basics so like the terminology and what's key. But if you're doing a specific problem, I would say, hey, just see how far you can get and then start pinging people from there.
Yeah, that's good. Okay. Yeah, I mean, because people that listen to this show are kind of all over the map. We have some people who are absolute beginners and some people that are listening to you and being like, yeah, I do what Pete does. So it's always an interesting mix as well. You try and give people a good basis to start from. When you approach a problem though as well, so say like let's just use the Bluetooth example there.
Yeah.
When you approach a problem, does it start from a place of practical, or does it start from more of a place of math? Like, and you specifically as a
definitely
as an
practical. So like, okay. If I need to put a Bluetooth antenna in a product and there's no constraints, like it's some plastic small thing and I can do whatever I want, then you don't need anybody with any level of intelligence, right? It's simple.
All right.
Like the rule number one.
This sounds like me.
do not make anything hard that does not need to be hard. Yeah. So like there's nothing wrong with going to DigiKey, typing, Bluetooth antenna or whatever, putting that on your PCB and then following like the keep outs for what's on the PCB, like that works.
Yeah.
So there's no reason that you don't need to do that. And Bluetooth is kind of pretty robust in the sense that, if you're only trying to go 10 feet, you're going to have more than enough link budget. It's not going to be that big. Don't make it hard.
Got it.
But it's like when you start like packing multiple systems in a product or you have very small keep out, you're trying to, you might have like metal in the product. That's when things can get very difficult, Okay. It's like when you're really trying to integrate a lot of different systems or really push the envelope on tight integration, that's when it becomes hard.
Right.
But just if someone's like, hey, let's put a Bluetooth antenna in a product, that doesn't necessarily need to be hard. It could be very simple.
Okay. Yeah, that's great advice then. And I think that the hard stuff like you were talking about, it sounds like that's kind of what you get paid for as an antenna designer, as an antenna engineer. You're digging in, you're probably still applying a lot of that practical knowledge that you have, but then you're like, okay, now we're in a corner case and now we have to do testing and now we have to do this and that.
Yeah. Well, the one piece of math is, whatever technology you're using, Bluetooth, GPS, cellular, you want to know like what the lowest frequency is that you're using. So if GPS is 1.575 gigahertz or whatever. So the antenna engineer immediately thinks, oh, okay, that's like 3.5, 3 3/4 inches or whatever for a half wavelength. So I'm immediately thinking, okay, that's about the size that I need for a decent radiator. So if someone comes in with like a product the size of like a quarter and they want GPS in there, then
right.
I know they're going to have huge efficiency problems.
Got it.
And so efficiency, by the way, is just your ratio of how much power you're putting into the antenna versus how much it actually radiates.
Okay. Yeah.
That's the key parameter in antennas is efficiency.
Right. And that's probably also pushing back into like how much like if you're on a plane, right, and you have, a generator on board, you probably have a lot more power available than like a tiny Bluetooth device, right?
Up to like, again, FCC limits, right? So you can't take it Bluetooth device and put out 2 watts, for instance. It won't let you do that.
Right. I just mean that, like, if you have a 10% efficient antenna, and you have to put in like a watt in order to get out 100 milliwatts. Like, you're burning 900 milliwatts in that case, and you could do it even with a low efficiency antenna, right?
Yeah. For Bluetooth, you're fine. Okay. The link budget, we're talking like a decent link budget for Bluetooth is like 100 dB. Because you might have plus 10 dBm output power. That's 10 milliwatts, and the sensitivity on the other side is minus 90 dBm. Mm-hmm. So, you can get away with a lot of, sketchiness a little bit. And then you mentioned something about percent. So that leads me to a rant I must give is everything in RF is dB. So you have the output power, dB, dBm, whatever. And then you have the loss or the path loss. It's always like 90 dB or something. Then you get to the RF side then you have an LNA with 10 dB of gain, and then insertion loss of a filter of 3 dB. And then you get to the antenna, and all of a sudden it's percent. So that, to me, I don't like it for that reason. So I always say antenna efficiency in dB. Just because everything is dB. So I don't know why they use percent. So really it should be antenna efficiency, it should be insertion loss or whatever. And then the other thing I don't like about efficiency is if you're talking to someone and they're like, oh, how much will this change affect your antenna? They'll say, oh, it's just a couple percent. That actually doesn't mean anything, because if you're going from like 2% to 4%, that's 3 dB. But if you're going from like 90% to 92%, that's nothing.
Right.
So so for those two reasons, I'm always like, no, don't say it in percent.
Yeah, that's good. That's good to know. And I've been reading that book, I think I mentioned on the show, by Tom Lee, the Planar Microwave book, and he brought up something there as like dB is always capitalized because the B is Bell, as in like Alexander Graham Bell. And I was like, oh my God, like that one little thing. I was like, oh yeah, that makes a ton of sense. I was wondering why it was like that. So capitalize your B's, folks. Yeah. So, I mean, and so you work in, decibels all the time. I mean, is that kind of how you think about the world now in terms of like the...
Yes, including like meetings. Scale? Like I'll be like, this meeting is 3 dB too long. So like, I use dB for almost everything.
Okay. How does that end up impacting like your... Are there any times when you, aside from what you said, like the efficiency stuff being like percentage and that, is there anything else in the field that is linear or non-logarithmic like that?
In RF, it's like literally all dB. Yeah.
Okay.
Can't think of anything off the top of my head.
Yeah, I'm just switching into that mode for me has been interesting. Like thinking about it like that, because it's kind of foreign just in terms of like thinking like that. But it's there obviously it's filter theory too. It is other places, but it's it's a little bit foreign for me, and switching into that mode is tough. So, so on the so going back to Boeing, like so now we're talking about a plane. You've got 20 different antennas on there. Yeah. So now you as an antenna engineer, what does your daily kind of task look like? Is it are you designing custom antennas? Is it testing what's out there?
So at Boeing, you don't really design the antennas. So we'll be like, okay, here's a system with a big radar, and here's a system that's a receiver. If we put them, like on these two locations on the fuselage, then the isolation will be, 60 dB or whatever. So then we can feed that information over, and they're like, okay, we can either get enough filtering or we need more isolation between the antennas, which means change the placement and try again. Or figure out, like, hey, these two systems aren't going to work at the same time. So let's not even try to use 100 dB of filtering. Let's just blank one or the other.
Okay.
So, So that's kind of an example.
And so like blanking, you mean like when one's on, the other one has to be off, that kind of thing?
Correct.
Okay. That's cool. And you mentioned you never really design antennas.
At Boeing, yeah.
Oh, okay. Is that because
a lot of antennas I put a lot of antennas in products, so...
Oh, okay. Yeah, we'll definitely get to that too. Why is it not the case at Boeing? Is it because of the constraints on the design itself?
I guess you don't necessarily. I mean, you don't need to design an antenna because, um, like, if you're putting an antenna in an iPhone, there's no way you can type iPhone antenna into Google, buy one, and then start using that. For instance, like it's integrated into the chassis, into the product. You have to factor in every component in there when you're designing it. Whereas at Boeing, you can type, "Hey, I need a 1 to 18 gigahertz circular polarized spiral antenna." Um, you can type that into Google and get a few different options, and then buy it and take it from there.
Okay.
So it's kind of like, yeah, you can make things hard, but you don't necessarily need to.
Got it. So if it was like a very, very, very tiny airplane, then maybe you'd have to do it because you'd be etching the antenna onto the wing or whatever it is. But because in this case it's huge enough that you
Potentially,
just
I
buy
mean,
one.
if you were like, look, there's no, like, I only have this size window for the antenna. We cannot find that, so therefore we need to design our own. That's a valid reason.
Okay. All right. Yeah, it is kind of like coming into shape of like the constraints you're dealing with. It's like other stuff being in the way, the total size you have, the frequencies you're working with. Are there other constraints that you thought about at Boeing that maybe you didn't have to think about at the consumer level products?
Um, well, the power is much higher
Okay, sure, yeah.
for radars, so they have different like classes of amplifiers and all that. I don't know, like in consumer, you're always much more worried about FCC limits, whereas like if you're working on the defense side, they don't have that as much.
Right.
They get their own frequency bands and
That's right.
have
Yeah.
their own GPS frequencies and all that.
Oh, I didn't actually know that. Okay,
Yeah, there's like military band for GPS.
that's cool. Okay.
Yeah.
Yeah, that's good. And then what about like, so you had mentioned like the polarization and like the directionality of an antenna as well. Like when you say you are Googling around and you're shopping for an antenna, like is it how is that kind of decision making process made, at least in that case of
Okay, so the first thing is, do you want a high gain antenna? And so, if you're working at Boeing and like you're communicating a point-to-point link and you know the direction of the other antenna you're communicating with, then yes, you want high gain. If you're making a router and it's talking to an iPhone, you don't want the iPhone or the router to have a high gain antenna. And that's because high gain means directional. And so if you don't know where the other side is, you kind of just want to spew energy everywhere.
Okay. And
So gain...
can you define the high gain in that context as well? Because I think about high gain just generally of like, okay, you're adding power to this thing, but you're saying it more of a like a directionality and like a focusing.
So gain specifically is efficiency in dB plus the directivity in dB. So for an example, you have efficiency of -3, directivity is always positive. Let's say it's 6, then your gain is 3 dB. So -3 plus 6, gain is 3.
Okay.
So like in consumer, high gain is like more than 6. And the reason gain is actually bad is, one, you're making the antenna more directional, which isn't great. You don't want it to work in one direction and not another. And then the other is just FCC cert. So like a lot of the rules require like, okay, your radiated power in a certain direction must be less than some level. So if you have a really high gain on your antenna, then that's bad, because then you might have to back off how much power you're transmitting because your gain is too high, and that's bad.
Yeah. Okay. And then so you're saying that because you would just be spewing it in the one direction, that you would have to take everything down total because
FCC. So they'll be like, okay, the limit is 30 dBm at, so usually like you might have a problem at 5 gigahertz because it's the smallest wavelength, which means the antenna is the largest at that frequency, which means the gain's the highest. So typically, like the larger your antenna is, the higher the gain. So if you want a really high gain antenna, you need a big antenna. Does that make sense?
I think so. Yeah.
Okay. So because 5 gigahertz is the highest frequency, typically like for Wi-Fi, that has the smallest wavelength, so the gain is always higher at 5 gigahertz than it is at 2.4 gigahertz, for instance. So like FCC might say, oh, the peak gain is 30 dBm that we're allowed or the peak radiated power is 30 dBm, which they call EIRP, equivalent isotropic radiated power. They make it complicated for no reason, but that's basically conducted power, which is how much power is coming out of the radio, plus your antenna gain. So if, for instance, you have 8 dB of antenna gain and you're trying to transmit 24 dBm, then you're over the limit and you have to back off the conducted power. And that's bad because you don't actually have antenna gain. The antenna is a passive device. You're always radiate less power than what's coming out of your radio. So if your conducted is 24 dBm, you're only, your antenna efficiency is -3, you're only radiating 21 dBm. But you still could be over the EIRP limit, which is what they require you to be at. So you have to back off the conducted power. So you have less radiated power coming out. That's bad.
Yep. Also, wanted to disambiguate as well. So you've been saying dBs and dBm, and that always confused me as well. So that's dBm is 1,000 dBm, less? Or
it is context based, but so when you say dBm, you're always referring to milliwatts in power. So 30 dBm is 1 watt, 0 dBm is 1 milliwatt, 10 dBm is 10 milliwatts. But when you're talking about antenna gain or efficiency, those are always dB because it's a strict ratio. There's no antenna efficiency of dBm. That doesn't make sense. It's always dB because it's ratio of input to output power.
Yeah, that's good. That's good to have that as people are listening to. I'm sure that a lot of this too is all right, well, go and read on the Antenna Theory website. That's just good for this kind of stuff. But no, that's good. Just as we're talking about these things. Okay, and that's a great point about the FCC stuff and how that kind of impacts things in consumer versus the military stuff. Yeah. Are there ever? So you said antennas are always passive, so it's always about adding power before that with an amplification stage. Is that right?
Yeah. Okay. Yeah. So at least in consumer, RF and antenna team is 2 different teams.
Okay.
So RF team focuses on the board level, which is the radio, all the amplifiers and all this. And then the antenna team focuses on the antenna. So there's a strict DMZ, demilitarized zone between the 2 teams where they focus on the board level, we're focused on the antenna.
Interesting.
And so antenna team works more closely with product design than mechanical engineers because we're really integrating that antenna, and it's a function of, all the grounding around it, the screws, the flexes, all these things. RF team might work more closely with the EE team.
Right, delivering power, having clean power, that kind of thing.
Yeah, but the RF team and the antenna team don't necessarily need to interact too closely. I mean, again, on the certification thing, where the peak gain has to be below, that's an example where they would need to communicate. But RF team focuses on measuring all their parameters in a 50 ohm system.
Okay. And
the antenna team measures the antenna in a 50 ohm system. When you hook it up, if both teams get it right, it just works.
Got it. Okay, and that's good to know as well. So that's another thing I've been learning from this book as well. I've read it before and heard it before, but like I said, I haven't been working with it all that much. But the working with 50 ohms as well, I didn't know the origin of that 50 ohms in the past.
Yeah, it has to do with power handling and loss, the trade-off between the 2 or something, right?
Yeah, I think there's one of the parameters 30 ohms is the optimum, the other one 70 ohms is the optimum, so they just split the difference and said 50.
Yeah.
It's fun. That's cool. Okay, so you kind of started talking into the consumer side of things. So after Boeing, you went over to Apple, and obviously a ton of the constraints changed. So what was that like?
It was wild. Going from a place like Boeing, which they have a union for the engineers and product cycles are on the timelines of 10 years, to Apple where it's 1 to 2 years. And, that was crazy. I was just wow, things move really fast here. So that was the biggest thing there. But yeah, it was just it was totally different. It was we designed the antennas at Apple. They have an antenna team internally that starts with, hey, we want to put an antenna on this new product. Let's figure out what we need to do. And there's no custom antennas that it has to be custom because they're always coming up with crazy industrial designs for everything.
Right.
You can't, that's a very good case where you cannot go to DigiKey and buy an antenna and put it in a product and call it good.
Yep. And so, okay, so let's talk about maybe the prototyping process and kind of like walk from prototype through production if you can.
Okay.
So
so let me go high level, like
Sure,
consumer electronics. Let's say this is how it works. So in general, so near the top, you have the industrial design team. So they're the ones who are like, we want the computer to look like this and to have this materials, to feel like this and do this. In conjunction with like the product team, which is like figuring out the business case. But so essentially it starts with industrial design. They have their vision. Like they want an all metal product. No gaps anywhere.
No.
Right? Yeah. So then, from there, they give it, the product design team, which is mostly mechanical engineers, start like figuring out, okay, how would we make this thing and all this. At the same time, then like antenna team will start working with similar material like mock-ups. So it's like, okay, let's say you're doing a computer. And they're like, we want metal in all these regions. And you're like, well, we're going to need a gap somewhere for the antenna. So if they provide no gap at all, then you have to like kind of start.
Right. You're like, this is a land-based product now.
Yeah. Or, like one thing you have to do is like if there's literally no space, you just put in an antenna and do your best. And then you say, hey, look, so given this, the best we could do is an antenna efficiency of minus 20 dB. It's just not going to work.
Wow. Okay.
Yeah. So, sometimes like, you have to do that. And then, in a healthy relationship, there's give and take. And, you say, okay, well, we'd be willing to move some metal away here. Can you get this to work? And so it starts, there's a lot of iteration, I guess.
Negotiation too, huh?
Negotiation, but yeah, I mean, if everybody's aware of what the goal is, like for instance, in cellular phone, you can't ship an antenna that has like minus 10 dB efficiency because they have like the carrier set specs. It's like it must radiate this much power, so you can't just squash it. So you can't ship it like if you just completely ignore the antenna. So
okay. So now you're at the point where you have an industrial design. You've negotiated a little bit of plastic or a little bit of a cutout so that you can get an antenna through.
Yeah, and you would have you would at that point you wouldn't just say, oh, I think it would make it work. You would have like a mock-up or a simulation that says, hey, given these volumes, here's what we're going to hit. We're committing to that. Once you're there and you're comfortable, then, or at least everyone's on the same page, then. Then it's about integration, which is, again, just as much, probably more work than the design itself. So the integration is like, okay, well, now we're going to throw in the speaker. And, so you learn like what things are the biggest risks. So a speaker is a lot of, plastic and air. So those kind of interact well with the antenna. So if you open up like, phones, you'll see like the speakers and the antennas coexist in the same locations. Yeah. And then like, oh, okay, we're going to need the power cable is going to go here. What happens when we plug in the power cable? Does it destroy the antenna? What can we do about that?
Because it's a channel of metal, you're saying?
Exactly.
Yeah.
And then, you just start figuring out like, okay, where do like you have like the metal on the back of the display, for instance, and the metal on the camera, like where are the critical ground points? That need to be in there such that the antenna doesn't get degraded as we start, making this from like a kind of a mock-up that's just the shell to an actual product.
Yeah. And you mentioned simulation, so that I'm sure that's kind of like you keep revising that throughout time. But what are you using to simulate?
So personally, I'm not a big simulator, but the most common ones are HFSS and CST, I'd say. Yeah, I mean, so I think simulation is good. You always have to confirm it with mock-up because there's no way you can, capture like all the, like you might have some loss inside a flex that you can't capture in simulation. You really need to build it and test it to ensure that. Or like let's say you have a piece of foam grounding, how do you know that foam is, making the proper contact when it's actually in the product? You can't simulate that as well as you might hope. So simulation is a valuable tool. Like definitely I shouldn't say it's not. But you definitely have to confirm
Yeah.
simulation with the mock-up.
Yeah, it's like a starting point versus the be all end all kind of thing.
Yeah. So some people don't simulate at all; they just go straight to the mock-up because they're like, "Hey, why do I need to do it that way?" And that works. And some people, do it where they rely more heavily on simulation. There's no right way. It's kind of like what people want to do based on their experience. And if you can ship products and you've done it before, then hey, whatever works for you. Right?
So when you're doing you say you're not doing that much simulation like you do. So what is the alternative then? So it's you have a mock-up, you have test antenna in there, and then you just kind of throw it on the bench, or what are we talking about here?
Yeah. So you'll like pick a product like.
Let's use it like an iPhone if you don't mind talking about that. That'd be great.
We'll talk about a Samsung phone.
Okay, Samsung phone. How about a generic Android phone?
Yeah, we're going to talk about a Windows phone. So let's say
that sounds great. How about a Nokia brick phone?
Yes. So you have a Nokia phone, yes. Nokia Windows phone, and it's on your desk. So first of all, there's not that many fundamental types of antennas. Like they're all basically like hybrids of dipoles, and like a dipole is basically two wires that are in phase and hence radiate. And you start with that, and you start like meandering it to fit in the package. And basically, if you've worked in antennas, like if you're designing a cell phone, you should have, and you didn't have exposure before, you would buy like 10 different cell phones, tear them down, and figure out what's working. Measure the antennas on those. You'll start to gain some knowledge. You won't have a lot of knowledge because you can tear down like a phone doesn't mean you know what's the critical points in there, like which ground points are critical, which volume, and like which components of the volume, like the height or the width, are absolutely critical, and which flex really needed choked, and all this different things. So you start to learn by doing. But when you're working at Nokia, they give you a phone, and you're like, hey, I negotiated this volume. You would essentially just cable it out, which means put a cable on the antenna, ground it to the PCB and all that. So your cable is not influencing the measurement. First thing is you put on a VNA, vector network analyzer. That's where you can see the impedance. So that'll tell you like if it's tuned properly. So like if it's GPS, you'll say, hey, the impedance goes to 50 ohms or whatever. And then like basically you'll hear antenna people talk about VSWR, or that's just basically the return loss. Like a VSWR of 1 is perfectly matched. So basically you're looking at a plot of VSWR versus frequency. You see, it goes down and it's matched at this frequency, so I can tune it up or down. That first thing just tells you the antenna is accepting power. It doesn't actually tell you it radiates. So there's two things for an antenna to radiate. It has to have a structure that supports radiation, and it also has to be matched at 50 ohms. So with the VNA, you can tell, hey, it's matched. And so we're delivering power to the antenna. But it could also just be absorbing that power. Like if I put a 50 ohm resistor on a VNA, it'll be like, oh, it's really well matched. Because it just,
right.
So once it's matched, once it's matched, then you would measure, you just go straight to measuring the efficiency. And that's done in an anechoic chamber. So it's just basically, you already have it cabled up, the antenna cabled up in the product. You put it in an anechoic chamber, which measures like how much power is coming out from every direction, essentially, integrates over it and tells you, hey, this is how much power came out. And that's your efficiency.
That's great.
So if you know the efficiency, and then that's done at, whatever number of frequency points you want, but you have your frequency, your efficiency, and your impedance, and that's it. From there, you start iterating. So then,
like the frequency, the different frequencies is also interesting to me. So like this Windows phone, it's going to have maybe 2.4 gig for Bluetooth and maybe 5 gig for Wi-Fi as well, like more advanced Wi-Fi. But then also like a bunch of cellular frequencies and GPS frequencies. How do you get them all? Is it all one package, or like how do you start to cut all these things together?
So Wi-Fi is, at least for the last 10 years, always 2.4 and 5 gig. Typically on these phones, Bluetooth and Wi-Fi share the same radio and the same antenna.
Yep.
GPS is 1.575 gigahertz. That's usually 50-50. It's its own antenna or shared with Wi-Fi or cellular. So there's typically, you know the bands coming in. So it'll be like, okay, we need GPS, Wi-Fi, there might be NFC, and cellular. And they'll tell you the cellular bands. So if you're shipping a phone in the US, it actually used to be much simpler before LTE. There's only like 5 bands. Since LTE came out, it's so complicated.
Like 15 plus
no,
bands.
There's so more. You're like, I defy anybody working on a phone in 2019 to tell me all the bands that are on their phone.
Oh, really?
Actually,
okay.
Somebody will call me up, an antenna designer, and you can list all the bands on your phone. I'd be pretty impressed. No, it's crazy.
Okay.
But anyway, for an antenna engineer, it doesn't matter because you're like, okay, well, that translates to this set of frequencies. And so therefore we have to hit this set of frequencies.
There's is like 1750 or 1800? Is that one of the, 1.8 gigahertz? Is that? Yeah. So that's like one of the frequencies, right? But does it need to be just that one frequency, or can it be like sensitive over, from the 2.4 or the 1 gig up to 3 gig or something like that?
Yeah, I mean, you could make an antenna sensitive across a ton of bandwidth. That's good. You don't lose anything.
Good. Okay.
Yeah.
Okay.
You don't lose anything. You might need some filtering there or whatever.
Okay. So it's not the job of the antenna to reject anything. You're saying you're just trying to make the best transmitter
Correct.
Available, kind of.
Exactly, because filters do a way better job. Antenna is like slow roll off versus frequency, so you do not use the antenna you don't rely on the antenna for rejection. You have to rely on the filtering.
Got it. Okay.
But yeah, so you mentioned like 1850. So yeah, so in that spectrum, like just say 1850, like when I say there's so many bands, like there's probably like 10 different bands that sit on 1850.
Yeah.
There's like 2G, 3G, 4G, 5G now, like all these CDMA, all these different ones that sit on the exact same frequency. And then there's like the EU is slightly shifted from
That's right, yeah.
US.
Like 1900 versus 1850 or something. I remember I used to deal with these a little bit more, but there's a lot.
6-7 years ago, like iPhone 1, 2, 3 time, there was only like 4 bands. It was
wow.
You had like 2G bands, 2 3G bands. That was about it.
So does that end up impacting you other than you have to double check that you make sure you're testing for each of these bands and frequencies? So
if you have again, in the old days where you just had 2G and 3G, that just translates into some frequency range you have to hit. So it's like the low band was 824 to 960 megahertz, and that included US and EU, and then the high band was 1710 to 2170. So you would just say, okay, these are the frequencies I care about, and therefore I need the target is minus 3 dB efficiency across all those frequencies, and then you don't care. It's okay, they can do 2G, 3G, 4G, I don't care, it doesn't affect me.
Got it.
But with LTE now, there's so much bandwidth that they can't, it's really tough to cover all that. So there's antenna tuners, which are essentially switches, where you can you think about an antenna's resonant frequency as a function of its length. So you could switch in a longer arm or a shorter arm to change the frequency, for instance.
So it's almost like an old school radio where you're actually turning the dial and it's actually moving a slider onto something, but it's doing that with digital. And tapping
essentially, yeah. And then there's also impedance match tuning where you might put a series cap or switch in a shunt inductor or something, and that's another way to tune. But
that's really cool. And so when is that kind of decision made? Is that made during the antenna design phase? Yes. Okay, we're going to have 20 taps.
20 would be it's not like that. It'd be 3 or 4.
I'm pulling many things out of my rear today, Pete. Yeah. So just remember that.
Yeah. Again, if you start adding a lot of complexity, you're gonna have a lot of extra loss in there. It's gonna be too complicated. The big goal is you pay people a lot of money to keep things simple.
Okay. Yeah. Yeah. That makes sense.
Make stuff hard that's not good.
Yeah.
But yeah, so antenna design should be fully signed off before they start going to a proto build, for instance. You just say, I have these switches in place to cover these bands. These are the locations I have. These are the critical points. So we're ready to go.
Mm-hmm. And
you don't build a prototype or start making units and they're we have to add a switch. That would be pretty sloppy.
Got it. Okay. And so, like in prototyping kind of stage, like what is a prototype? Is it a prototype antenna just copper on flex PCB, or is it printed onto something, or is it part of a circuit board? Like, what does it look like in prototype, and then kind of moving up towards production?
There's different ones. So yeah, the earliest ones, like you could 3D print, like let's say somebody wanted to make a phone that's like a triangle or something. Like you could 3D print that triangles, like copper tape out where the PCB is, and that's kind of your ground plane. So the ground in the PCB is also like part of your antenna.
Okay.
So yeah, the antenna doesn't just sit alone by itself. That's why you buy an antenna off DigiKey, for instance. It'll say like, hey, you need a ground plane this size, because that's part of the antenna. But yeah, so you could 3D print, a triangle, lay out copper tape for the ground plane, and then say, okay, well, I'm going to give myself 8 millimeters in this direction for my antenna keep out, and just start, cutting copper tape in there and then measuring it as you go. Like that's a valid way.
Okay.
You could also simulate it, whatever you want to do.
Okay, that's good. That's good to know. And then, how do you start to like take the other stuff in the field of not the field of view, but I guess it's the radiation field of view or whatever it is called. How do you deal with like a hand on a cell phone or a head on a cell phone? Like, how do you deal with that kind of thing?
So there's a certain amount of like loss that they expect in that case, but so like the carrier will have specs like, hey, you have to radiate this much power when the phone's by itself. When you strap it to someone's head, you radiate this much power, and they might reduce the limit by 3 dB or something.
Mm-hmm.
But the way to test is, they just sell like, so your hand is just basically a little bit of loss, high dielectric. So you can buy like materials that's similar.
Like a fake hand?
Yeah, you can buy a fake hand or a block, whatever, and just strap it to the product and measure the efficiency again.
Okay.
So, it doesn't have to be hard. You could also simulate.
Yeah. What about the shape of an antenna itself? So, like, I'm thinking with copper tape, at least, it's like planar and very flat. There's some thickness to it. But like, how does that end up impacting the shape of like not the shape, but I guess the radiation patterns out of this thing? Is it always meant to be like the same, like unidirectional radiation?
Yeah. So ideally you would want that. So, and again, the unidirectional is kind of like a donut pattern. So that would be like the lowest. So like when you buy an antenna that says Omni, what that means is it's actually like a donut shaped pattern. There's no perfectly spherical antenna radiation patterns. They don't exist. But yeah, so you look at a phone. So the low band, like let's say it's like 800 megahertz, the half wavelength is like 6 inches or whatever. The phone itself is less than a half wavelength at the lowest cellular frequency. So I already know no matter what the antenna designer does, it doesn't matter. It's going to have low gain, low directivity, which means the pattern's going to look kind of like the donut. So it doesn't even matter.
Well, isn't one of the techniques of like folding antennas back on themselves and stuff though as well?
Yeah, you can meander them, but you're still not going to end up with like the super directive antenna. You can't do it. At the higher frequencies, the phone, instead of being like less than a half wavelength, it's like might be 2 wavelengths long. In that case, the pattern starts to shift, and they shift in pretty predictable ways. Like, I didn't work on the iPhone 10 in front of me, but I could tell you what the low band radiation pattern looks like because I know the size of it. I know like the high end of the spectrum where the phone might be 3 wavelengths long. I know it's like the radiation pattern bends back towards the display in a certain direction. And I don't know anything about how they designed it.
Yeah. Okay. That's interesting. Like you kind of start to see the matrix for radiation patterns and such.
Yeah. Actually, I interviewed at Apple and someone asked me, I was like, what's the polarization on this antenna at low band? And I hadn't worked on cell phones. I was like, well, tell me what the antenna design is. And they were like, you don't need to know. And to answer the question. And I hadn't clicked till later. I was like, oh, okay, now I know why they were asking that. Because they know exactly what it should be. If I'd worked on this, I'd be like, oh, okay, the polarization is this way and the pattern goes like this. Doesn't matter like exactly what they did on the inside.
I'm not sure if we'll be able to explain that on audio only, but could you try and explain that a little bit more?
So antennas Well, like a phone antenna, the lowest frequency, it's fundamentally like a dipole, a half wavelength dipole. Like
Sure.
they want it to be. You might think it's more complicated, but it's really not. So one arm of the dipole is the whole back metal, which is like the display and the chassis that forms that, and then the other half is just like a small strip that's usually like if a phone has a lot of metal, it's actually that metal that is part of there. But there's no way to have a phone, like if you hold it upright, there's no way that the phone is going to be horizontally polarized at the lower frequency.
Oh, I see.
There's no way. It has to, like the current has to flow in the long direction. So
Right.
it's automatically, vertically polarized. Okay. There's no way to do it otherwise.
Okay. Yeah, that's good to know. That's good to know. So then, so you'd mentioned like, you have antennas that are across multiple frequencies as well. Are they usually, so say it is all one antenna, somehow you get it all in one antenna. Does that mean that there's just that single element and it is again just a dipole that's looks good for all these frequencies, or what does that look like?
Yeah, so there are definitely like you can make an antenna that will cover like, for instance, 824 to 960, and then that'll be the low band. The same antenna will cover like 1710 to 2400. Like that's definitely been done and doable. So there's rules in antennas. I mentioned one of them, which is like the half wavelength. Another rule in antennas is like more volume. The more volume you have, the more bandwidth you have. So when we talk about like a thin dipole, like just two wires, that's a pretty low bandwidth device. But you could really increase the bandwidth if you start making that dipole wide. So
just thickening up the width of that strip, you're saying?
Yeah, and not just making it a wire anymore, but like think about it like as a like a whole ground plane for each arm. When you start doing that, your bandwidth really gets large.
Yeah. Well, why is that relationship there? I guess I can't.
Why does more bandwidth equals? I guess like fundamentally, it's just if you think about like you have a very thin wire that's or two wires that form a half wavelength dipole. There's only like one fixed current mode that can fit on that. There's no like degrees of freedom for the current. Oh. But if it's almost like you have thickened things up, the current has extra paths to go, the resistance drops. Well, it's the same for radiation. Like you give it extra degrees of freedom for where the current can flow, and there's more modes or more frequencies can kind of fit on that structure and give rise to radiation.
Oh, that's interesting. Yeah, I mean, because at the end of the day, like you're saying, it is current. It's current moving back and forth, and then that causes radiation to happen. But you're saying that it would be like the equivalent of putting like multiple thin wires next to each other, right?
Essentially.
Yeah. And I like never thought about it like that. That's really cool. So now we've done prototyping, we've cut up copper tape, we've tried out different things. What happens then when you're like, okay, you go to production, or you go to even more, you go to FCC testing? How do you modify things as an antenna designer? Like, did you go in with like an X-Acto knife? You're like, yep, snip, 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 or like
a lot of times, yes.
Yeah.
So like, yeah. So once you have a prototype, if it's a mock-up, from there, like you got to integrate everything. Like I said, like all the flexes, like the battery, it's not a, that's going to have a connector on it and all these different things. You have the battery, the camera, mic flex is just flexible PCB, the button. Like you're gonna have a button right in the middle of your antenna volume, typically.
Windows phones have more than one button, so I don't know what you're talking about.
So you have all those, in there. So it's just you keep going with higher degrees of fidelity with a mock-up. Eventually, like when they build it, when I do the first prototype build, it's like a first form factor. It's kind of like the way the product works, and all the teams have their functionality in place, so everybody could. It's the first time everything comes together. At that point, you'll just measure the antenna exactly as I said before, where you cable it out, measure VSWR, measure the efficiency. And typically you'll find like, oh, it's lower than you expect, and you start figuring out why. And that process is just like, okay, I think maybe this flex or this component here is causing me a problem. Very simple. You rip it out, you measure it again. Oh, look, there's 2 dB loss due to that. What can we do to mitigate it? So that might be, then you start like, okay, we need a ground point here, or we need to choke this line. So a choke is just, like a inductor or something on a line that will pass the low frequency and, ideally block or choke the RF frequency. So if the current doesn't flow at RF, it's not going to eat the efficiency. So, that's like an example of a mitigation technique.
Okay. Yeah. So there's a lot without having to cut, you can just add something in, you're saying.
Correct. And so like early on, you might have experience with different things and add like placeholders, like, oh, we might need chokes on these lines and we're really going to need grounding here. Or, this is a risk. And so there's a few like builds where you're getting that integration right. And then inevitably things are changing. So at the same time, like the reliability team and the product design team, they have their own specs. Like they want to drop the phone from a meter and it should, like, bounce. Hey, four of them broke. And it's because now we need to thicken up this piece here. So then you work with them like, hey, they're like, hey, we're going to change this. And you have to like factor that in or say, okay, yeah, that's fine. No big deal. Or, okay, well, that screws this up. We got to figure out a different way. There's a lot of that. And then by the time you're at CERT though, you start testing CERT right away so you can figure out like, what all the issues are. But yeah, I mean, it's basically like every day you're coming in and trying to find the problems, fix them, get ahead of it. And,
yeah, and it sounds like a lot of like revision tracking type of stuff as well, because things are migrating. Like you how far behind the leading edge of the design were you? Like, were you closer to the production side of things or closer to the design side of things when you're moving?
Design for sure. So yeah. So it's a lot of work between the initial concept to getting something ready for production. And then, we'd be like, antenna engineer would typically be at builds close to production, sometimes production, but they shouldn't be there at the production build. That's owned by operations team whose goal is to figure out how to make, from one production line that works, how to make 30 production lines that work and track all these things. Right.
You have a golden unit they're comparing against probably anyways, right?
Yeah.
Okay. Well, you keep mentioning VNAs, and we alluded to it at the beginning of the episode as well. But you built your own VNA, and I'm not sure if you were using it at work, but you were definitely using it. So
yes.
Could you go through your what it was real quick and why you decided to build one?
Yeah. So I worked as an antenna engineer in consumer electronics, and like there's one lab I worked. Everybody had antenna VNA on their desk. And, we come in because it was our primary tool. And I was always looking at them. I was like, why is it so big? Why is it so expensive? They charge like $40,000, $50,000, $60,000. The cow kit is like $10,000. And I never quite understood that. Because meanwhile, we're building like, phones that are like $600, but, have much better screens and all this. And then like, I knew that like my phone interacts with the antenna in such a way that it can measure all the magnitude and phase of what's coming to it, because that's how digital communication works.
Right, yeah.
And the VNA was essentially doing the same thing, although a lot more, I guess, sensitive.
Right.
And so, it was something I was like, you know what? I was like, I bet I could build a VNA, or I want to build a VNA. Actually, I went to Maker Faire, and there was this guy who was showing like really simple VNA designs that, I went and built at first, which weren't very practical or very reliable, but that's kind of what got me started. I was like, you know what, I'm going to do this. And I didn't know anything about, like microcontrollers or I'd never done PCB layout and all this. So that was the basis of a talk at your Hackaday thing that I gave that's online if anyone wants to see it. But I go through like the whole process. I was just like, look, if I'm going to build a product, I need to do A, B, C, and D. And I just wrote it out. And it was like stuff I'd never done, like learn how to blink an LED on a microcontroller, learn how to, do PCB layout. And then like, I need to make a proto here that accomplishes these goals. And I just made a schedule and then just started knocking it out. It was actually really fun. I learned a ton. And I had a much better
I point people to that talk. Well, I just like, the fact that you kept like just saying like, well, and then I just went and figured this thing out. And I'm like, yes, that is awesome. Like, like you did, you just, you kind of went through and you figured out you needed to do a thing like blink an LED, but like each iterative step then was just getting you towards that end goal. But you had the goal in mind too, which was really a good start.
Yeah. I mean, and just like being able to make a board where I put a microcontroller on there, talk to a program it to flash an LED. Like when that LED blinked for the first time, I remember just being like,
oh yeah,
so happy. So I was like,
dopamine
if I can
like
blink
crazy.
that LED, I was like, I know how to do the next like 30 things because now I'm controlling this guy. It's like it's on.
Yep. That's great. So what are some of the baseline elements that are in a VNA that you had to actually design? Was it all like buying chipsets and having them kind of do the heavy lifting, or?
Somewhat. So the problem, or I guess the hard part, is to measure the impedance of something at RF. You kind of have to measure like the reflected wave. So impedance and what's reflected from the antenna are the exact same thing. Because like there's an equation that relates the two. So like if you have a 50 ohm line and a 60 ohm antenna, for instance, the reflection coefficient is determined. So if you measure either the reflected wave, it's the same as measuring the impedance. So to get the reflected wave, you have to have a thing called a bidirectional coupler, which essentially like, you're pushing energy to the antenna, but the energy that comes back is what's reflected, and you have to be able to pull that out of the same line. So the bidirectional coupler, basically siphons off some of that reflected energy. And to get that right over a pretty wide bandwidth is pretty tough.
Got it.
So that was a lot of iterations where I was trying, like, you can buy couplers on DigiKey that are cheap or make printed ones on circuit boards that kind of do the same thing. So that was pretty challenging. That's probably one of the fundamental things in the VNA.
That's like what you're paying for in a good VNA kind of.
I have no idea what's in there. I've never done a teardown.
You're afraid to take apart your expensive piece of gear.
Yeah. So then, you have, amplifiers. You have a frequency synthesizer, for instance, which is another cool little. So you can just buy like a frequency synthesizer that'll work like from 10 megahertz to 6 gigahertz or whatever. And you just program it with MCU, or you're saying, hey, I want this frequency to come out, and it does. It's really cool.
That is, that's great.
So the frequency synthesizer puts out the frequency. So like when you want to measure a GPS, for instance, you just say, hey, put out GPS frequency, and then you measure the reflected wave. And
okay, so you're outputting so you're generating a signal 1.575, whatever it is.
Whatever,
you have to.
Typically, you do a sweep over whatever range, but yeah.
Okay. But in the instant you're outputting this frequency, you have to amplify it as well. Yep. I'm guessing
you don't necessarily need to, but yeah, you can. Depends on
Then you push it out, and then the coupler is what actually allows you to siphon off, like you said.
Yeah. So you put an antenna in there. Once you plug an antenna to your VNA, you automatically have reflection there. And that reflection.
How do you discern what is reflection versus what you're actually sending out? Because it's all on the same line, right?
Yeah, so there's basically like a coupled line in there that's designed in such a way that they have a parameter for the coupler that happens to also be called directivity, and it measures like how much more sensitive this line picks up the forward versus the reverse traveling wave. So like a good bidirectional coupler might have a directivity of 30 dB, which means like the reflected signal is 30 dB stronger than the forward traveling wave. So, so a lot of it, if you type bidirectional coupler into DigiKey, you can pull up some spec sheets and start looking, and that's pretty much how it's spec'd out.
That's pretty cool.
So,
then the stuff that you siphon off, that is the reverse, the stuff coming back, then that just goes into ADC, or what are you actually doing to actually measure that then?
So that then you need to know basically the relative phase to the forward wave, because you need magnitude and phase. And so then, there was a chip that would output like a voltage that was proportional to the magnitude, and a different voltage that was proportional to phase. And then, I would just ADC those lines and get like essentially the value for the complex reflection coefficient. And once I have that, I can immediately know the impedance.
That's great.
And so, so fundamentally it's simple. It's like you're sweeping through different frequencies, you're stepping through at each step, you measure the magnitude and phase of the reflected wave, and then you get the impedance.
Yeah.
Yeah.
I mean, you make it sound simple, and then you even showed it how to build one, and it makes it sound kind of simple too. But it's like, damn, there's a lot of stuff in there.
Yeah, and then my big goal was to get it on Kickstarter. I got it on Kickstarter, but yeah, the demand wasn't there. So
Yeah.
so I think that's kind of learned why they're so expensive. One is like to get a really high bandwidth thing, like you need a lot of switches in there, a lot of getting everything exactly right. Like it is pretty challenging. It's not like, oh, I'll make a VNA done.
Yeah.
And then it's just it's not like phones where you're gonna sell 20 million a year. You're gonna sell like 200 a year.
Right.
So
right. And you're like already competing in the lower end market versus something higher margin. So
yeah. So ultimately I met the goal of putting it on Kickstarter, offered it for sale, got a bunch of orders, which was cool, but didn't hit the target. So I decided, hey, I got my VNA. I'm keeping it. That's enough.
That's great. And you still use it?
Yeah, I do. Yeah.
That's great. How does it compare to what is the frequency range of the VNA that you built?
It's like 400 megahertz to 2.7 gigahertz. So if I'm doing like, Bluetooth or something, or cellular, like low band cellular, high band cellular, I can do that. But yeah, it's just mainly at my house. It's super light, which is cool. Like it's the size of like, like a big iPhone. Whereas like, professional VNAs are so big, you're going to have to hurt your back.
Right.
So.
Yeah, that is nice to be able to, and like, probably bring it to a meeting and pull it out and show someone and they'd be like, wait, what is that?
Yeah.
That's great. So, I mean, you're doing consumer level stuff now. I mean, like you mentioned, there's, VNAs are a big tool there. Are there other tools that you find yourself using on a daily basis that people should know about?
I mean, besides rework equipment, like, if you're an antenna engineer, you need to be able to solder O201s and such for your impedance matching. And, but yeah, so if you have a anechoic chamber, you can measure the efficiency. If you have a VNA, you can measure your impedance. And also if you have multi-antenna systems, you can measure the isolation, which is like if you put in energy into one antenna, how much does the other antenna absorb?
Okay.
That's another important parameter for multi-antenna systems. But yeah, VNA and a chamber is fundamentally all you need. You could also add simulation tools if you want.
How big are the chambers that you would use on just testing versus like a FCC certification type thing?
So they can be pretty small. Like there's a company, Satimo, that makes one that's only about a 9-foot cube, and that one, so that's a smaller one. But it will do cellular. So the size of the chamber you need is really a function of the wavelength again. Okay. So if you're doing like 60 gigahertz millimeter wave stuff, you might need like a chamber that could fit on a desk. It's much smaller. But yeah, the ones in consumer typically use are, 9 to 13 feet on a side for a cube.
Yeah, like room sized.
Yeah. FCC, they get really big, like 5-meter chambers, and that's just because they measure super low frequencies. Like you got to measure the radiated emissions at 2 megahertz.
Yeah.
So
I always figured that was because they also drive like bigger things, and they might have like larger devices in there as well. But I guess that's well, that's pretty cool. Well, Pete, what else should we know about you and antenna theory and your background? Is there anything else we missed?
Geez. I don't know.
Your whole life, just like condensed down to an hour.
Yeah, I'm working on putting a rocket on a balloon.
Oh yeah,
lighting the rocket when the balloon's up. So I made a Raspberry Pi that battery powered Raspberry Pi that just waits for a certain amount of time and then just turns on a switch, which fires a little igniter, which I'm going to put on a rocket that's on a balloon. So that's a project I'm working on.
Okay. And the rocket is going just up further, or what's the deal?
Yeah.
Okay.
So, like, I don't understand why. So the biggest thing in rockets is even bigger than gravity is wind resistance. And it's like when you get to 100,000 feet, it's like less than 1,000th, I think, the air density.
And what's that in dB?
So, 30 dB.
There you go.
But yeah, that's a good catch. So I had this idea, and it turns out other people have had the idea and done it. But So I'm kind of doing something that's been done before, but
no reason not to do it though. That's cool.
Yeah, so like little things, like I put a GoPro on the balloon and it has to work. It's like minus 40 degrees in there, so I make sure I run my GoPro in my freezer and figure out how to insulate it. So I literally have a GoPro in my freezer at home, and I'm like recording to make sure what type of insulation will keep it working longer.
That's great.
So I do a lot of stupid stuff like that.
No, it's super fun though. It's super fun.
Yeah.
And like, are you just trying to get the rocket higher to get like more curvature out of a picture kind of thing?
Yeah, there's not a super big goal right now. It's just like, I've wanted to do the balloon experiment, which people do where you can take a balloon up to 100,000 feet and then it pops, a parachute goes and you go and get it. So I don't do that. And then the rocket is I got into rocketry as well. It's kind of fun. And just combine the two. Natural.
That's great. And plus, the antennas are going to be really good on those things, phone and home.
They're going to be fantastic.
Well, Pete, this has been great. Where can people find you and more about you online?
Go to antennatheory.com. So everybody, if you're like, hey, what you said here wasn't right or don't agree, want more information, feel free to ping me. My email's on the website. But yeah, this is my 2 cents on antenna engineering. It's my take based on my experiences.
That's great.
Thanks for having me. It's fun.
Yeah.
It's like chatting about antennas. So.
Yeah, well, definitely. I'm probably going to give you a call sometime soon with lots of questions to bend your ear about it. So.
Okay. Cool.
All right. Thanks, Pete.
All right. Thank you.
Once again, we'd like to thank our sponsor, Roden Schwartz, a leading manufacturer of value instruments designed to help you maximize your bench's performance for everyday applications. They just announced an industry first, complete solutions with all the upgrades upfront for one price. Now through December 31st, save up to $10,000 on Roden Schwartz solution packages that come with fully loaded test and measurement instruments right from the start. When you invest in Roden Schwartz products, you get the highest quality engineering, plus all the bandwidth, channels, inputs, memory interfaces, and signal generation you'll ever need. Learn more about Roden Schwartz value instruments and this limited time promotion at askanengineer.us. That's askanengineer.us.